Hey everyone, welcome back to AI Paper Podcasts. Today we're diving into a paper that's making waves in the world of AI and mathematics. Gold medalist performance in solving Olympiad geometry with AlphaGeometry2.
It's truly fascinating work.
So for our listeners, this is AG2, and it's not just solving these complex Olympiad-level geometry problems.
It's actually outperforming the average International Math Olympiad gold medalist.
That's right.
It's achieving an 84% solve rate on IMO geometry problems.
From the years 2000 to 2024.
Exactly, building on its predecessor, AlphaGeometry, but with some serious upgrades that are pushing the boundaries of what's possible in automated mathematical reasoning.
So for those keeping score at home,
AG2 boasts an expanded domain language, a faster
and more robust symbolic engine called DDR2.
a novel search algorithm named SCAFSTANCE,
And it's all powered by
a Gemini-based language model.
But what's really exciting is not just the solve rate.
It's how AG2 cracks these problems.
We're talking about solutions that are, in many cases, more elegant and creative than what humans come up with.
And later on, we'll
Delve into some specific examples of AG2's superhuman creativity.
highlighting specific solutions from IMO 2024 and other challenging problems.
Right.
The paper is structured in a pretty standard way for this kind of research, starting with a deep dive into AG2's enhanced domain language. One of the limitations of the original AlphaGeometry was its restricted language.
Limited vocabulary.
Yeah. And the researchers addressed this head-on by adding new predicates and features to handle a wider range of geometric concepts.
So they basically gave AG2 a bigger vocabulary to work with.
Exactly. Think of it as equipping the system with more tools to describe and reason about geometric relationships.
Okay.
This expansion allowed AG2 to express things like movements, linear equations, and locus theorems, which were previously out of reach.
So previously, it just couldn't handle these.
No, and this alone increased its coverage of IMO problems from 66% to a whopping 88%.
That's a huge jump.
Yeah.
It really highlights how important language is, even for an AI tackling geometry.
Absolutely. The language allows AG2 to move beyond simple number crunching and engage with geometric reasoning on a level closer to how human mathematicians approach these problems.
Yeah.
And it's not just about the language itself. The researchers also automated the process of problem formalization and diagram generation.
That used to be manual and time-consuming bottlenecks.
Yeah.
So previously, someone had to translate the problem into AG2's language and draw the diagram.
Right, it wasn't very efficient.
That doesn't sound very efficient.
It wasn't.
Right.
But now, thanks to the Gemini Foundation model, AG2 can take a natural language problem, like something you'd find in a textbook, and automatically translate it into its internal formal representation.
Okay.
It even tackles the tricky task of generating diagrams for problems that aren't explicitly constructive.
I'm curious about that. How does it generate a diagram when the problem doesn't give you specific instructions on how to construct it?
It uses a clever two-stage optimization method that starts with a random diagram and then iteratively refines it to match the constraints described in the problem.
Okay, so it starts randomly and then kind of homes in.
And then it just keeps getting closer and closer.
Okay.
This automation is a game changer. It makes AI geometry solvers like AG2 far more practical for real-world applications.
I can see that.
Like, imagine architects or engineers being able to use a tool like this to quickly explore different geometric designs.
Yeah.
It could revolutionize those fields.
Absolutely.
The potential applications are vast.
Right.
Now, moving to the core of AG2's reasoning capabilities, let's discuss the symbolic engine, DDR2.
Okay, so this is where the AI really flexes its mathematical muscles.
Precisely. One of the key advancements in DDR2 is its ability to handle double points.
Yeah.
This means the AI can now recognize that 2 points with different names might actually represent the same location in the diagram.
I see. So it can identify situations where the problem is trying to trick you with different labels for the same point.
Exactly.
Okay.
This is a major leap in sophistication because it allows AG2 to tackle more complex geometric scenarios.
Right.
It's like an architect understanding that 2 lines on a blueprint might intersect even though they're labeled differently.
Yeah.
In addition to double points, DDR2 boasts a faster algorithm for finding similar triangles and cyclic quadrilaterals.
Okay.
These are fundamental geometric concepts.
Yeah.
And being able to quickly identify them is crucial for efficient problem solving.
It's like giving the AI an intuitive grasp of these key building blocks, allowing it to spot patterns that might take humans much longer to find.
Precisely.
Right.
And to top it all off, they implemented DDR2 in C++ up, a much faster programming language.
Makes sense.
This makes the entire Symbolic engine significantly more efficient. We're talking about order of magnitude speed improvements.
Wow.
Which is essential for exploring larger search spaces and finding those elegant solutions.
So they've given AG2 a bigger vocabulary, automated key processes, and supercharged the Symbolic engine. What else have they done to push the boundaries?
Well, they also focused on improving the training data, which is crucial even for a system like AG2 that relies on symbolic reasoning. You can think of it like training an athlete. You need to provide the right kind of mental workout to achieve peak performance. In this case, the researchers significantly improved the methods for generating synthetic training data, which means the data is richer, more diverse, and includes a wider range of problem types, including those challenging locus problems.
Which involve?
That involve moving points and lines.
So like they've designed a training regimen for AG2 that covers all the bases, preparing it for any kind of geometric challenge it might encounter.
Exactly.
Okay.
One of the interesting choices they made was to stick with random diagrams as seeds for their data generation process.
Okay.
This might seem counterintuitive, but it actually helps avoid data contamination and allows for a wider exploration of possible theorem distributions.
I see.
The resulting training data is impressive. Larger, more complex diagrams, longer and more complex theorems and proofs, more balanced data distribution across different question types, and even the inclusion of those tricky locus problems I mentioned.
So they're ensuring that AG2 is exposed to a wide range of geometric situations and problem-solving strategies.
Right.
How did they generate those locus problems, though? Those could be pretty tricky to create.
They introduced a new movement dependency function, denoted as P, to control the relationships between moving points and lines.
Okay.
This function allows them to generate locus problems where the position of one point is dependent on the position of another, which adds a whole new layer of complexity to the training data. Plus, they developed a faster data generation algorithm that significantly speeds up the entire process.
Okay.
This means they can generate even larger and more diverse data sets to train AG2 on.
It sounds like they've really gone all out in terms of training data quality and quantity.
Yeah.
But even with all that data, you still need an efficient way to search for solutions, right?
Right.
Especially with complex geometry problems where there can be many potential paths to explore.
Absolutely. And that's where their novel search algorithm, SCAFSTANCE, comes into play.
Okay.
SCAS stands for Shared Knowledge Ensemble of Search Trees.
Yes.
And is one of the most innovative aspects of this work.
Okay.
It's like having a team of AI mathematicians working together, each exploring different approaches and sharing their insights to solve the problem faster.
That's a really cool analogy. Can you break down how SCAFST actually works? What are these search trees and how do they share knowledge?
Each search tree in SCAFST represents a different strategy for exploring potential solutions.
Okay.
Some trees might focus on constructing specific auxiliary points, while others might prioritize applying certain theorems. This variety ensures that AG2 covers a wide range of problem-solving approaches.
Okay.
And the knowledge-sharing mechanism is truly ingenious. As each tree explores a particular path, it records any useful facts it discovers in a shared database.
I see.
So if one tree hits a dead end, the others can learn from its experience and avoid wasting time exploring the same fruitless path.
That's brilliant.
Yeah.
It's like they've created a collaborative learning environment where the AIs are constantly pushing each other to be better. I'm guessing this significantly speeds up the search process.
It does. The parallel exploration combined with the knowledge sharing leads to significant improvements in both search efficiency and robustness. They've even got different types of search trees running in parallel,
Okay.
each with its own unique configuration.
Right.
Some use classic beam search, while others specialize in predicting multiple auxiliary points or uniformly sampling different auxiliary point types.
Okay.
They're also varying the depth and breadth configurations of the trees to ensure a comprehensive exploration of the solution space.
It sounds incredibly sophisticated.
Yeah.
How do they manage all these parallel processes and ensure they're working together effectively?
The system design is actually quite elegant.
Okay.
The language model, or LM, and the DDR workers operate asynchronously, communicating through a shared queue.
Okay.
The LM proposes potential actions, like constructing an auxiliary point, and the DDR workers evaluate those actions,
Okay.
updating the shared knowledge base with their deductions.
Okay.
This asynchronous approach allows for efficient resource allocation and prevents any single worker from becoming a bottleneck.
Okay, so we've covered the domain language, the automated problem formalization, the symbolic engine, the training data, and the search algorithm. What about the language model itself? We know it's based on Gemini, but have they made any specific modifications or enhancements to tailor it for geometry problem solving?
Yes, they have. The language model plays a crucial role in AG2's success. They've simplified the training process to a single phase
Okay.
and experimented with various training setups, including training from scratch, fine-tuning pre-trained math models, and even incorporating diagram images into the training process. They've also moved away from greedy decoding,
Okay.
which tends to get stuck in local optima, and instead adopted top-stack sampling during inference.
So instead of always choosing the most likely next step, the language model considers a range of possibilities.
Exactly, which is probably essential for finding those creative, out-of-the-box solutions that AG2 is known for.
Yeah.
And they've introduced a really interesting concept called the analysis string,
Okay.
which is basically a way for the symbolic engine to share its deductions with the language model.
Okay.
It's like giving the language model a cheat sheet that highlights the key insights the symbolic engine has already figured out.
That makes sense. It allows the language model to focus its energy on the parts of the problem that still need to be solved, making the whole process more efficient.
Precisely.
Right.
The analysis string contains information about facts that are deducible from the premises, facts that are deducible from both the premises and the goal, and even numerically correct facts. This gives the language model a much richer context to work with when proposing new actions.
Right.
For example, it might help the language model avoid proposing auxiliary points that would lead to contradictory deductions.
It's a really clever way to leverage the strengths of both the symbolic engine and the language model.
Yeah.
So with all these improvements in place, how does AG2 actually perform? Does it live up to the hype?
It absolutely does.
Okay.
As we mentioned earlier, AG2 achieves an impressive 84% solve rate on IMO AG50. A benchmark dataset derived from all the IMO geometry problems from 2000 to 2024.
Wow.
To put that into perspective, that's better than the average IMO gold medalist.
That's incredible. Are there any results broken down by year or problem difficulty? I'd be curious to see how AG2 performs on the more recent and challenging problems.
Yeah, they provide a detailed breakdown of the results in Table 4 of the paper.
Okay.
It's worth taking a closer look at those numbers to see how AG2 stacks up against other state-of-the-art systems and human benchmarks. One particularly impressive result is its performance on IMAZEL AG30,
Okay.
a set of 30 very difficult IMO shortlist problems that have never appeared in the actual IMO. AG2 manages to solve a significant portion of those,
Really?
which really highlights its ability to tackle complex and challenging geometry problems.
That's remarkable. It sounds like AG2 is truly pushing the boundaries of what's possible in automated geometry problem solving. But I'm sure there are still some limitations, right? No system is perfect, especially when dealing with the intricacies of high-level math.
You're absolutely right.
Right.
While AG2's performance is truly groundbreaking,
Yeah.
it's important to acknowledge that it still has room for improvement.
Yeah.
For instance, the current version of AG2's language doesn't cover certain types of problems,
Okay.
such as those involving inequalities or a variable number of points.
So there are still some geometric concepts that are beyond its grasp.
Okay.
What about the problems that fall within its language capabilities, but that it still couldn't solve? What were the stumbling blocks in those cases?
That's a great question. The researchers dug into those unsolved problems and found that they often involved advanced geometry techniques that aren't currently implemented in AG2's symbolic engine.
Okay.
Things like inversion, projective geometry, or the concept of radical axis.
It's like AG2 hasn't learned all the fancy moves yet,
Right.
but with its track record, I wouldn't be surprised if they incorporate those techniques in future versions.
I agree. The researchers are already exploring ways to expand AG2's capabilities further.
Okay.
One particularly interesting direction they're looking into is the potential for language models to generate full proofs on their own without relying on an external symbolic engine like DDAR.
That would be a huge leap.
Yeah.
It's like asking if the AI can truly think for itself in the world of geometry,
Right.
crafting logical arguments from scratch.
Exactly. And they've already made some interesting progress in that direction, but we'll delve into those details in the next part of our deep dive.
Sounds good.
Welcome back to AI Paper Podcasts. We're continuing our deep dive into AlphaGeometry2.
All right, so before the break, we were talking about AG2's impressive performance on those challenging IMO problems and hinting at some of the future directions the researchers are exploring. One thing that really caught my attention was this idea of language models potentially generating full proofs without relying on a symbolic engine like DDAR.
That's definitely one of the most thought-provoking aspects of this work. Imagine an AI that can reason through a geometric problem from start to finish, constructing a complete and logically sound proof all on its own, without relying on an external tool to handle the symbolic manipulations.
That would be a game changer. It'd be like witnessing a machine truly understanding mathematics, not just crunching numbers or applying algorithms. How did the researchers even begin to assess whether that's possible?
They took a multifaceted approach. First, they developed tools to verify the logical correctness of individual proof steps generated by the language model.
Okay.
This is crucial because you need a way to check whether each step in the AI's reasoning is valid. It's like having a meticulous proofreader scrutinizing each line of a mathematical argument.
Makes sense. Did they create a separate data set of proofs to test this capability?
Not exactly. They used the same AlphaGeometry2 data, but instead of having the symbolic engine generate the proofs, they tasked the language model with generating them. Then they applied their verification tools to analyze the proof steps the language model produced. They categorized the errors they found, ranging from simple syntax mistakes, which are like grammatical errors in a sentence, to more complex logical fallacies, which are like flawed reasoning in an argument.
So what were the results? Was the language model able to produce any fully valid proofs on its own?
The results were actually quite encouraging. Even at this early stage, they found that the language models, even without the help of DDR, made very few syntax errors.
Okay.
This means they were able to generate grammatically correct mathematical statements, which is a good starting point.
That's promising. But what about the actual logic of the proofs? Were the steps logically sound?
The majority of the steps they generated were either fully verified as correct by the tools or were deemed logically sound, but lacked complete verification due to limitations in the verification tools themselves.
Okay.
This means the AI's reasoning was often on the right track, even if the tools couldn't definitively confirm it in every case.
So it's like the AI is showing glimpses of genuine mathematical reasoning, even though the tools aren't quite sophisticated enough yet to fully assess its capabilities.
That's a great way to put it. It's like we're catching glimpses of a new form of mathematical intelligence emerging, but we're still developing the tools to fully understand and appreciate it. This suggests that future AI systems equipped with more advanced language models and more powerful verification tools might be able to reason through math problems entirely on their own, producing complete and logically sound proofs from scratch.
That's an exciting prospect. It would open up new avenues for mathematical discovery and could even change the way we teach and learn math. But for now, it seems like the combination of a language model and a symbolic engine like in AG2 is still the most effective approach.
That's right. The symbolic engine excels at handling the precise symbolic manipulations, while the language model provides the higher-level reasoning and strategic guidance.
Okay, so we've explored the potential for language models to generate full proofs. What are some of the other research directions the authors delved into while developing AG2?
One interesting area they investigated was the role of tokenizers and domain-specific languages in AG2's success.
Let's break those down one by one. First, tokenizers, for those who aren't familiar. Can you explain what a tokenizer is and why it's important in this context?
A tokenizer is essentially a way of breaking down text into smaller units that a language model can understand. Think of it as the alphabet of the language model's world in natural language processing. We often use tokenizers that split text into words or subword units, but when dealing with mathematical expressions, things get a bit trickier.
Right, because mathematical notation has its own unique syntax and structure. It's not like a regular sentence.
Exactly. So you might assume that you need a specialized tokenizer designed specifically for mathematical language to achieve good performance in a task like geometry problem solving. And in fact, that's what the researchers used in the first version of AlphaGeometry. They used a tokenizer that was specifically tailored to handle mathematical symbols and expressions.
So for AG2, did they stick with that specialized tokenizer?
That's what you might expect, but they actually decided to experiment with something different. They wanted to see if modern large language model tokenizers, which are designed for general language, could handle the complexities of mathematical notation without needing any special modifications.
That's a bold move. It's like throwing a natural language tokenizer into the deep end of the mathematical pool and seeing if it can swim. What were the results?
Surprisingly, they found that the choice of tokenizer didn't significantly impact AG2's ability to solve IMO problems. This is a really interesting finding because It suggests that the latest generation of LLM tokenizers, even those trained on massive text datasets, are flexible enough to handle the nuances of mathematical language without needing any special handholding.
That's impressive. It means we might not need to create specialized tokenizers for every math-related AI task, which could simplify development and make these systems more accessible.
Exactly. Now let's talk about the domain-specific language itself. AG2 uses a language specifically designed to represent geometric concepts and relationships. You'd think that this strict formal language would be essential for the AI's reasoning abilities, right? It provides a clear and unambiguous way to express geometric ideas.
That's what intuition would suggest. It's like giving the AI a precise set of tools to work with, eliminating the ambiguity and vagueness of natural language. Did the researchers ever test whether that assumption holds true?
They did, to explore the role of the domain-specific language. They conducted a fascinating experiment. They translated all of the AlphaGeometry2 data from its formal language into natural language.
So they were basically asking, can the AI understand geometry problems written
Right.
in plain English?
Exactly. It's like giving the AI a geometry textbook written for humans and seeing if it can still grasp the concepts and solve the problems. And the results were, again, quite surprising. They found that training a language model on natural language data led to similar performance on IMO problems compared to training on the formal language data.
That's remarkable.
Mm.
It suggests that the AI is able to extract the underlying mathematical meaning even from less formal representations. It's almost like it's developing its own internal understanding of geometry that transcends the specific language used to express it.
Precisely this finding has significant implications for the future of math-related AI systems. It means we might be able to leverage the power of large language models pre-trained on massive text datasets without needing to painstakingly translate everything into a formal language. This could significantly reduce the time and effort required to develop these systems.
That's a huge win. It could open up new possibilities for applying AI to solve real-world problems in fields like physics engineering and economics, where the problems are often expressed in natural language rather than formal mathematical notation.
Absolutely. Now, building on that last point, the researchers also wanted to explore whether fine-tuning a language model pre-trained on math data could further enhance AG2's performance.
Okay, so instead of starting from scratch, they're taking a language model that already has some mathematical knowledge and giving it specialized training on geometry problems.
Exactly. They took a Gemini model that had been trained on public math datasets, which included things like mathematical equations, proofs, and word problems. Then they fine-tuned this model on the AlphaGeometry data, which is specifically focused on Olympiad-level geometry problems.
It's like giving the AI a crash course in advanced geometry, building on its existing mathematical foundation.
Yeah.
How did this fine-tuned model fare against the models that were trained from scratch on just the AlphaGeometry data?
Interestingly, the fine-tuned model didn't necessarily blow the other models out of the water. It performed on par with smaller models trained from scratch, and the 3.3 billion parameter model trained from scratch. So while starting with a math-specialized model didn't provide a clear advantage, it also didn't hurt performance.
So it seems like both approaches have their merits, but did the fine-tuned model exhibit any unique strengths or weaknesses compared to the other models?
That's where things get really interesting. Even though all the models were trained on the same AlphaGeometry data, they each developed slightly different strengths and approaches to solving problems.
So it's like each model has its own unique problem-solving style, even though they were fed the same information. That's fascinating.
It is, and this diversity turned out to be a valuable asset. Remember, SCAFSTANCE, the shared knowledge ensemble of search trees that we discussed earlier, well, by combining these different models, each with its own unique strengths, into the SCAFSTANCE framework, the researchers were able to achieve even better overall performance.
So it's like having a team of mathematicians with complementary skills, each bringing their own unique perspective and problem-solving approach to the table. The diversity strengthens the team as a whole.
Precisely, this highlights the importance of exploring diverse training approaches and model architectures in AI research. It's not always about finding the single best model. Sometimes the real power lies in combining different strengths and perspectives.
Absolutely. Now, before we move on to the next section, I want to touch on one more research direction that the authors explored, and it's one that I find particularly intriguing, incorporating multimodal learning into AG2.
Right. This is where things get really interesting, and it ties back to our discussion about tokenizers and domain-specific languages. As you know, AG2 is built upon the Gemini 1.5 model, which is inherently multimodal. This means it can process both text and images.
So the researchers wondered if they could leverage this multimodal capability to give AG2 an even deeper understanding of geometry by allowing it to see the diagrams alongside the text descriptions.
Exactly. They trained a new set of models that took both the problem text and the corresponding diagram image as input.
It's like giving the AI a visual aid to help it grasp the geometric concepts more fully. Instead of just reading about a triangle, it can actually see a triangle with all its angles and sides. Did this multimodal approach lead to any significant performance gains?
That was the hope, but the results were a bit more nuanced. While the initial results during training looked promising, they didn't observe a significant improvement in the solve rate on IMO problems when using this multimodal model alone.
So it wasn't the magic bullet they were hoping for?
Not quite. However, just like with the fine-tuned math models, the multimodal model brought its own unique strengths to the table. It produced slightly different auxiliary point proposals compared to the text-only models.
So once again, diversity proves to be valuable. Even if a particular model doesn't outperform the others on its own, it might still contribute valuable insights when combined with other models.
Exactly. By incorporating the multimodal model into the SCAFSTANCE framework alongside the other models, they were able to boost the overall performance. The multimodal model's unique perspective, shaped by its ability to process both text and images, added a new dimension to the team's problem-solving capabilities.
So even though the multimodal model wasn't a star performer on its own, it contributed valuable insights to the team effort. It's like having a team member who might not always come up with the best solution individually, but who consistently asks thought-provoking questions and challenges the team to consider new perspectives. Their presence elevates the entire group's thinking.
That's a great analogy, and this raises some really interesting questions about how we can best integrate multimodal learning into AI systems for solving complex problems. It's not always a simple matter of adding more data modalities. We need to carefully consider how those modalities interact, complement each other, and contribute to the system's overall understanding and problem-solving abilities.
Right. It's not just about throwing more data at the problem. It's about thoughtfully integrating different types of information to create a richer, more holistic understanding. Did the researchers offer any potential explanations for why the multimodal model didn't achieve the gains they initially expected?
They did. They delved into the nuances of the problem and identified a few potential factors that might have limited the multimodal model's performance. One key observation they made was that IMO problems often involve very intricate diagrams, which can become visually cluttered and difficult to process, even for humans.
It's like trying to find a specific detail in a Where's Waldo picture, but instead of colorful characters, you're dealing with geometric shapes and lines. It can get overwhelming quickly.
Exactly. The image tokenization process, which breaks down the image into smaller units for the AI to process, might also be a limiting factor. It could be that the tokenization process is losing some crucial spatial information that is important for understanding the geometric relationships in the diagram.
So it's like trying to understand a puzzle after someone has jumbled up all the pieces.
Yeah.
You have all the individual components, but you've lost the crucial information about how those pieces fit together to form the complete picture.
Yes, precisely. And they also pointed out that some of the visual information might already be implicitly present in the text descriptions of the problems. For example, if the problem states that two lines are parallel, the AI doesn't necessarily need to see those lines in the diagram to understand that relationship.
Right, the text already encodes that crucial piece of information, so the visual representation might not be adding that much value in those cases.
Exactly. And finally, they highlighted a really important point that often gets overlooked. The core of geometry problem solving often lies in algebraic reasoning rather than purely geometric reasoning.
What do you mean by that? Aren't geometry problems all about shapes and diagrams?
Well, yes and no. While geometry certainly involves visualizing and manipulating shapes, many human IMO contestants rely heavily on computational techniques like complex numbers, barycentric coordinates, or trigonometry to solve geometry problems. These techniques often involve manipulating algebraic expressions rather than directly visualizing geometric relationships.
So even though it's called geometry, the key to solving these problems often lies in abstract algebraic thinking.
Precisely, and this suggests that while visual information can be helpful, it might not be the most crucial ingredient for achieving breakthrough performance in this domain. It's the ability to translate geometric concepts into algebraic expressions and manipulate those expressions effectively that often unlocks the solution.
Fascinating. Okay, so we've covered a lot of ground in this part. Exploring the potential for language models to generate full proofs, the role of tokenizers and domain-specific languages, and the challenges and opportunities of incorporating multimodal learning into AG2 in Part 3. We'll wrap up our discussion by highlighting some of AG2's most impressive solutions and discussing its overall implications for the future of AI and mathematics.
Sounds good.
Welcome back to AI Paper Podcasts. So far, we've delved into the technical intricacies of AlphaGeometry2, from its enhanced domain language and symbolic engine to its innovative search algorithm and the exploration of multimodal learning.
We've seen how AG2 pushes the boundaries of AI and mathematics, but what really sets it apart
Is its ability to generate solutions,
that are not just correct.
but remarkably elegant and insightful.
Yeah, it's time to shift gears and witness AG2's superhuman creativity in action.
Exactly. This is the part I've been looking forward to seeing. An AI outperform humans on benchmarks is impressive.
Yeah.
But understanding how it achieves that level of ingenuity is where things get really exciting.
Absolutely. Let's start with IMO 2024, problem 4.
Okay.
This problem, as you might recall, involved a triangle, its in center, and some tricky conditions about tangents and circumcircles.
Right. You'd expect to see solutions involving trigonometry or complex numbers.
A problem that would typically have even experienced mathematicians reaching for their advanced geometry toolkits.
But AG2 surprised everyone with a remarkably simple and elegant approach.
I'm curious to hear how it tackled this one. What was AG2's strategy?
Instead of resorting to those advanced techniques, AG2 constructed a single, well-chosen auxiliary point and then used nothing more than similar triangles and basic angle chasing to arrive at the proof.
Wow, constructing a single auxiliary point to unlock a complex IMO problem.
I know, it's pretty incredible.
That's pretty incredible. It speaks to a deep understanding of geometric principles.
It really does, and the researchers who analyzed AG2's solution were particularly impressed by the choice of that auxiliary point. It wasn't a point that a human mathematician would likely have considered, yet it unlocked the problem beautifully.
It's almost as if AG2 is revealing hidden structures in geometry that we haven't fully grasped yet. It's a reminder that even in well-established fields like Euclidean geometry, there's still so much to explore.
I completely agree, and this isn't an isolated incident. AG2 has demonstrated similar ingenuity on other challenging IMO problems. Take IMO 2013 Problem 3, for example, which involved proving that a triangle was right-angled given some conditions about its excircles and circumcircle.
Okay, that one sounds pretty tricky as well. How did AG2 approach it?
Once again, it opted for an unconventional approach, constructing the midpoint of a specific arc as its auxiliary point.
Okay.
This led to a remarkably clean and insightful proof, leveraging a key cyclic relationship that most human mathematicians would probably have missed.
It's fascinating how AG2 consistently finds these elegant paths to the solution. It's not just finding answers.
It's finding beautiful answers.
Yeah, and it raises intriguing questions about the nature of mathematical creativity. What does it mean for an AI to exhibit elegance and ingenuity in problem solving? Is AG2 tapping into a different kind of intuition than we are?
Those are deep philosophical questions that I don't think we have definitive answers to yet. But AG2's achievements certainly force us to reevaluate our assumptions about what constitutes mathematical creativity and where the boundaries lie between human and artificial intelligence.
Yeah.
Absolutely. Now, there's one more solution I want to highlight that truly showcases AG2's exceptional problem-solving skills, its approach to IMAZEL 2009, problem G7. This problem was considered so difficult that prior to AG2, only computational solutions were known to exist.
And those computational solutions likely involve sophisticated techniques that most human contestants wouldn't even attempt during an IMO.
Exactly. But AG2 managed to crack this problem using a purely geometric solution, relying only on fundamental concepts like similar triangles and cyclic quadrilaterals.
That's remarkable to solve a problem previously thought to be solvable only through computational methods using just elementary geometry.
I know, it's really amazing.
It's a testament to AG2's ability to delve into the heart of geometric relationships.
Absolutely. So how did it do it? What was the key insight?
AG2 started by constructing a series of circumcenters, a strategy that at first glance seemed almost random and chaotic.
I can imagine it's not the kind of approach you typically see in a human-generated solution.
Right, but as the proof unfolded, it became clear that AG2 had a brilliant plan all along.
Okay.
Each circumcenter served a specific purpose, weaving a network of relationships that ultimately led to the desired conclusion.
So it wasn't randomness. It was strategic exploration guided by a deep understanding of geometric principles.
Precisely.
It's like watching a grandmaster chess player thinking several moves ahead.
Precisely. This solution beautifully demonstrates AG2's capacity for deep strategic reasoning and geometry, even without relying on advanced mathematical tools.
It's truly inspiring to see an AI system capable of such elegant problem solving. It's a testament to the power of fundamental geometric principles and the potential for AI to push the boundaries of mathematical understanding.
Couldn't agree more. It's almost as if AG2 is showing us new ways of thinking about geometry, unveiling hidden connections and patterns that we've overlooked.
Well said. As we wrap up our deep dive into AlphaGeometry2, let's step back and consider the broader implications of this work. What does AG2's success tell us about the future of AI and its role in mathematics?
AG2 serves as a powerful reminder of the rapid progress being made in AI, particularly in domains that were once considered exclusive to human intellect. It's pushing the boundaries of what we believe machines can achieve, and it's doing so with a level of creativity and elegance that's truly inspiring.
It's a paradigm shift in how we perceive the potential of AI. We're no longer talking about just automating tasks. We're talking about collaborating with AI to explore uncharted territories of mathematical knowledge.
Exactly. Imagine a future where AI systems like AG2 become indispensable tools for mathematicians assisting in research education and even the discovery of new mathematical concepts.
It's a future full of possibilities. AI could help us solve long-standing mathematical problems, uncover hidden connections between different areas of mathematics, and even lead to breakthroughs in other scientific disciplines.
It's an exciting prospect, and AG2 is a significant step towards that future. It's a testament to the power of human ingenuity in creating such a system and a glimpse into the transformative potential of AI in expanding the horizons of mathematical exploration.
Well said. For all our listeners who are eager to delve deeper into this fascinating work, you can find links to the paper and the remarkable solutions we discussed in the show notes. Until next time, keep exploring the ever-evolving landscape of AI and its impact on the world of mathematics.
Goodbye.